Thank you.
Thanks, Rishabh. So I guess I'll tell you today about a new candidate for obfuscation. And this is sort of a pretty significant departure from the existing schemes we have. And so if you haven't, if you zoned out of the recent works on IO, you should still be able to understand this talk. And the ideas are fairly simple. So I'll be able to explain the construction in sort of detail, which is actually pretty simple, which is an added benefit of this scheme. So let me get started. And also, the scheme is simple. And so if you have any questions, please interrupt and ask questions. I'm happy to elaborate and explain further. And this work is joined with Rika, Nico, and Julia. So let's get started. So, okay. So I'll start with some basic information, basic stuff about obfuscation. You probably know it, but just for the sake of everybody who, to keep so that everybody's on the same page. So the goal of obfuscation is to make computer programs unintelligible without affecting their functionality. So in particular, if let's say we have a party Alice and she holds a program P in her mind, and it could be in her favorite programming language, she would like to obfuscate this program and give the obfuscated version to Bob, such that Bob can execute now this obfuscated version on his computer, just as he could have executed the original program P. But Alice somehow wants to hide the secrets that were embedded inside the P from Bob, in particular, since Bob will have access to this obfuscated program. So defining obfuscation is not is not immediate, and in fact there was some it took some effort to define obfuscation, and here's sort of the most natural notion of security and definition for obfuscation. So we consider a randomized procedure O that takes as input a program C or a circuit C and outputs the obfuscated circuit O of C. And the functionality requirement is that the obfuscated circuit C should compute the same function as C, right? So if you want the obfuscated version to preserve the functionality, then there's the efficiency requirement that the obfuscated circuit should not be much larger than the circuit C, so which is more formally stated as obfuscated of C is at most polynomially larger than C. And the third requirement, which is the unintelligibility requirement or the security requirement, here we have multiple notions. And sort of the most natural notion is what Barak et al. Called the virtual black box notion. What this notion says is that for every adversary A, there exists a simulator such that for every circuit C, the obfuscated version of the circuit, if adversary is given obfuscated version of the circuit, that's equivalent to giving the simulator oracle access to the circuit and the size of the circuit. In other words, if I give the adversary the obfuscated circuit, it doesn't learn anything more than what it could have learned using just oracle access to the circuit C. Okay, so it's sort of a very natural notion, but unfortunately, in the same work, Barak et al. Showed that this notion is actually impossible to realize. In particular, they showed that there are circuits for which this notion is actually impossible. Okay, so they also introduced this slightly weaker notion of what they called indistinguishability obfuscation, which has had a tremendous impact in the recent years. So in particular, this notion is as follows. So if you have two circuits, C1 and C2, which compute the same function and are of the same size, then the obfuscation of one of them is indistinguishable from the obfuscation of the other. In particular, if I obfuscate one of these two circuits and give the obfuscation to you, you cannot guess which circuit was obfuscated. And this is true even if you have knowledge of both the circuit C1 and C2. Okay, so a point here to note is that inefficient IO is always possible. So in particular, the obfuscation algorithm could just take list all possible circuits that compute since we're looking at circuits that compute a particular function, could look at all circuits that compute the same function and output lexicographically the first function in that list, where the list is the lexicographic ordering is based on some fixed form. And this will give you an indistinguishability obfuscator, but the challenge here is that this is going to be efficient. And then sort of the main goal of cryptographic indistinguishability obfuscation is to make this this canonicalization efficient. Okay? So at first sight, this notion of indistinguishability obfuscation might seem rather weak, but sort of perhaps the strongest philosophical justification for why this is a good notion was provided by Goldwasser and Rothblum. And the idea is that if I take a circuit C, and these are the same circuit, I've written the same circuit twice. If I look at the best possible obfuscation of this circuit, and I look at the same circuit padded with a bunch of no operation gates, and was to use an indistinguishability obfuscator to obfuscate the two, then I cannot distinguish whether I obfuscated the best possible obfuscation or just the original circuit padded with a bunch of no operation gates. So we can therefore sort of this suggests that the obfuscation obtained by indistinguishability obfuscating a padded circuit is as good as the best possible obfuscation. And this sort of intuition is what provides the strength for indistinguishability obfuscation. That is, in whatever application we might be able to, where we might be interested in using obfuscation, indistinguishability obfuscation already offers whatever is the best achievable. Okay, and this is sort of the reason for a significant number of applications. And I won't go into the applications, just probably you've seen some of them at least. Functional encryption, deniable encryption, two-round MPC, and so on. So now, for the focus of this talk, I wanted to focus on just constructing obfuscation, which relies all these applications. And this is where there is a lot of work been since 2013, where we saw some of the first constructions for indistinguishability obfuscation based on multilinear maps. So there have been various lines of work that have emerged, but even the line of work from multilinear maps, there's been sort of immense amount of work. And this picture shows you some of these works that used multilinear maps to get obfuscation in all kinds of different ways. And there are a bunch of constructions, some in the standard model, some assuming specialized modeling of the multilinear maps. However, there were attacks both on the multilinear maps, and I'll talk a little more about it, as well as the obfuscation construction based on multilinear maps. But the bottom line is, in this space, we have some candidate constructions which are currently known to resist the known attacks on multilinear maps. I've stated here one as an example based on the GGH13 multilinear maps, but there are also candidates based on CLT 13 or CLT 15 and GGH 15 multilinear maps. The second line of work that has emerged is constructing obfuscation using these low complexity PRGs, and additionally standard assumptions, in particular the ones on bilinear maps and so on. So this is sort of the second line of work. It emerged by the effort sort of started with the realizing obfuscation constructions making little use of multilinear maps. So in particular, when original obfuscation constructions required multilinear maps with large multilinearity, and there was effort to reduce the level of multilinearity. Ultimately, we ended up at obfuscation candidates based on just bilinear maps and these low complexity PRGs. Okay? And there are other paths. For example, the Gentry et al. Construction, Gentry, Jutla, and Kane, which uses tensor product-based constructions. And then there are also attempts at constructing trilinear maps, for example, by Huang. Okay, so there are sort of there are other paths as well, but the first two that I mentioned, the multilinear maps and these low complexity PRGs, are the most popular ones. And sort of something common in all these paths, the two popular and the other sort of paths for obfuscation has been that all of them have gone via sort of starting with new or newish computational problems. So for example, the original multilinear maps started with these new assumptions on multilinear maps that were rooted in n2 assumption, but they assumed something stronger. Analogously, the special PRG constructions, they are also assuming something, special properties of these newly constructed pseudorandom generators. However, once we make those assumptions, these newish assumptions, the constructions themselves are proved based on these hard problems. Okay, so I say argued because these assumptions themselves can be a little, they're new and they're not as well understood. So I've said maybe argued, but the reductions are we can give proofs for them. Okay, and another sort of the problem with this these approaches, sort of all of them. While currently, in each of these categories, we have candidates which are known to resist, our current understanding of the cryptanalysis. However, they've sort of all gone through this break and repair cycle. So, for example, we saw attacks on multilinear map candidates by Coronatol and Hujia. There were also attacks by, for example, by MSC, and further on the obfuscation candidates based on multilinear maps. There were originally these sum of square attacks on the low complexity PRGs which were used for constructing obfuscation. So, and the similar is also true about the other parts. For example, the trilinear map candidate, we saw a break and repair cycle there as well. So for all these methodologies, while we currently have candidates where they resist known attacks, but they've all gone through this break and repair cycle. And while we're currently learning, there's sort of this maybe a sense that you have to start with some new assumptions and build on top of them to realize obfuscation. Okay, so you have to start with new assumptions, and maybe our understanding is limited right now. And as we go further, we break them and we repair them and so on. We'll ultimately get obfuscation schemes that we can, whose security we can rely on. Okay? So this is sort of the approach that has currently been taken. We make new assumptions, and we hope that we can get candidate constructions which will be secure. Okay. And the hope is ultimately, maybe we start with new assumptions, and maybe we can weaken the assumptions and get things from LW. However, this has not happened so far, but that's sort of the goal. Okay, and maybe this is essential, and part of the reason there is that we have some negative results. In particular, there's an impossibility result saying that you cannot get indistinguishability obfuscation for all circuits based on, let's say, if you had access to evasive obfuscation for evasive circuits. So, for example, if you could we already have lockable obfuscation from lattices. There is evidence that is not going to be enough to do obfuscation for all circuit, at least in even in a black box way, but even in sort of some non-black box way. So maybe this provides some evidence or some justification for why new assumptions are needed, and maybe this is the way to go. But there's sort of an alternate methodology that's often used in crypto. So there's this one methodology, right? We try to base things on concrete assumptions and so on. And then maybe we get started with assumptions which are sort of new, but hopefully, as we pin them down to something simpler and simpler, even if it's not something that's, completely standard right now, maybe over the years, we'll have built some confidence on them. But then there's this alternate methodology in crypto, which is sort of also proved to be immensely influential and useful, though it has its own caveats. And it sort of gives, there are two such examples of this methodology, which is sort of random oracle model, and the other being circular security. And there are clearly differences between the two of these, but I'm sort of putting these two sort of ways of constructing crypto primitives together because there's a heuristic aspect to both of them. Okay, so both the random oracle model and the way we can think of just take any encryption scheme and assume it's circularly secure. There's sort of both very heuristic in nature, where we don't give any proofs. But there's a distinction in how this methodology goes with respect to the first methodology of basing things on concrete assumptions. When we talk about a specific assumption, for example, LWE, we're sort of saying, look, this is secure. But when we're talking about circular security, we really don't have a finger first of all, we're talking about a heuristic that goes for not just one encryption scheme, but many encryption schemes, right? So you can assume any encryption scheme is circularly secure. And sometimes that conjecture might be true or sometimes might be false. And similarly for the random oracle model, if you assume that a hash function can be modeled as a random oracle, you're assuming something about not just one hash function, potentially many hash functions. And also you're not putting completely your finger on what the assumption is. So sort of this is very heuristic in nature. So there are shortcomings of both of them. We know constructions where the random oracle methodology has pitfalls, and similarly for circular security, we know encryption schemes which are not circularly secure. So in particular, when I give you an encryption of the secret key, we know that those encryption schemes are insecure. So we have, there is a room for error in this methodology. However, still, both these techniques have been very useful. In particular, for example, random oracle provides us with some of the most efficient signature schemes, in particular in terms of the signature sizes, unless you resort to to special assumptions. For example, indistinguishability obfuscation gives you short signature scheme, signature schemes with short signatures. But if you wanted to get something efficient, then this is sort of a very successful methodology. Similarly, circular security has been crucial to the design of fully homomorphic encryption schemes. So, for example, right now we don't know. We only know leveled homomorphic encryption schemes from lattices, and we have to assume circular security in order to get fully homomorphic encryption, which has had tremendous impact in cryptography. So these techniques, while heuristic, have had significant impact. And I wanted to spend some time on bringing this comparison, because the construction that I'm going to present is going to live within this framework. So we're going to use heuristics which sort of combine circular security and the random oracle model in ways which we don't clearly understand, and get an obfuscation construction, but at the same time we won't know how to break it. Okay? So that's so I see there's a question. Let's see. Yes, it does. And so the question is, does the evasive function imply something less powerful than witness encryption? Yes, it does. However, we know that even witness encryption is not enough as a black box, or even to some extent some non-black box, to realize obfuscation for all circuits. Okay. Hopefully that answers the question. If you have follow-up questions, feel free to type in the window or unmute yourself and ask. Okay, so let me move on. So the crux of this slide is that we're going to get an obfuscation construction where we're not going to make any new assumptions. We're going to make assumptions that we understand, but use them in ways that we don't. Okay? Just as we do for the random oracle methodology in circular security. Okay. So the advantages of this alternate approach is that we're not going to have to start with new assumptions. We're not going to have to start with multilinear maps or special PRGs or trilinear maps or anything new. We'll start with things that we can all agree or we have confidence in their security, and then we'll use them in sort of ways we don't understand. The second advantage is that we'll get a construction which is not going to be a one candidate. We're going to get a family of candidates. So we're going to say, if you have a generic primitive X, then you can, and you use it in some way, you get a obfuscation. So maybe you could find, and we have many natural, provably secure instantiations of X. Of course, the construction is heuristic, and so that needs further study. Okay, so in a nutshell, the result that we have is that we're going to start with certain homomorphic encryption schemes. These homomorphic encryption schemes are the ones that we're going to use are going to be based on standard assumptions. So we're going to have schemes which are already considered in the literature, and we're going to start with these schemes and combine them heuristically, and voila, we'll get obfuscation. Okay, so that's the high level result. To expand this picture, this is going to be done in 2 steps. So what we're going to do is we're going to take fully homomorphic encryption. So I said I started with homomorphic encryption schemes. So I'm going to use sort of 3 homomorphic encryptions, or homomorphic encryption scheme with sort of the three different flavors. The first flavor is homomorphic encryption with linear decryption, or fully homomorphic encryption with linear decryption. And this is something that we know how to construct. Virtually all FHE schemes that we know satisfy these properties. We're also going to start with a linearly homomorphic encryption scheme with split decryption. I haven't defined what split decryption is, but I'll get to that in a second. So that's the second flavor of a homomorphic encryption scheme that we'll use. And we'll also use candidate hash functions. You could use AES or anything that you like, but you can also construct them from a linearly homomorphic encryption scheme. Okay, so all these primitives can be constructed from homomorphic encryption schemes with certain additional properties. And I'll talk more about them in a minute. I'm going to combine them in some way to get something that we call split FHE. Okay, so note that I didn't define what split decryption was in linear encryption. I'm going to do that. It's going to be the same property for split FHE, and I've not yet defined it, and I'll define it in the next slide. Once we get this heuristic part out of the way, we can then say that once you have split FHE, then that provably implies indistinguishability. Okay, so the heuristic part of the construction is limited to the horizontal arrow in this picture, going from the homomorphic encryption schemes to split FHE. That's the heuristic part. That's what I'll spend most time on, and then that's what needs more investigation.
Sorry, Sanjam. Did you define what split FHE is?
No, I haven't, and it's on the next slides. But it's the same property as linear homomorphism with split decryption. But I'll define it in a second. Okay.
Okay.
Okay. So now let me answer Shafi's question. What is split FHE? So we all know what FHE is. It consists of 4 algorithms: keygen, enc, eval, and dec. Enc, and the property that FHE has is you can use the eval algorithm, which takes a ciphertext as input and a circuit C and outputs an encryption of the circuit computed on the encrypted message. So if I start with a ciphertext encrypting the message M, then I get back a ciphertext encrypting C of M. Split FHE does, as the name suggests, split the decryption algorithm. Okay. So what split FHE does is, instead of having one decryption algorithm, we're going to split it into 2 parts, the hint and rec. So I see some questions. I'll answer them once I finish the slide. The hint algorithm, what it does is it generates, so it takes a ciphertext and a secret key and generates a hint. Okay, so typically decryption takes the ciphertext and just recovers the encrypted message. And now we're splitting into 2 parts, where the first part generates a hint, and sort of think of the hint as a helper information to generate the decryption, right? So the second is the public reconstruction. So given the ciphertext and the hint, you can recover the message M. So you no longer need the secret key to decrypt the ciphertext, but only the hint. And you can think of it as the ciphertext dependent sort of secret key that's allowing you to decrypt. I mean, at this point, you might wonder, well, what's the purpose of the hint? The hint could be the message itself, right? So this is where this non-trivial efficiency requirement comes in, is that we want the hint to be much smaller than the size of the message, okay? So I have a large ciphertext. I want to help. I have the large ciphertext. You have a large ciphertext. I want to decrypt it and give it to you. So there's one way I can decrypt it and give you the message. That's one way of doing it. But I want to reduce the communication cost, and so what I do is instead I decrypt it locally. But when I do the decryption, I get something small, which is a hint, and I give you the hint, and you can now use just the hint to recover the message. Is this clear? If there are any questions about the split property, I can answer. I can also look at the chat and see if there are questions.
So why can't the hint be the secret key itself?
Good. So the hint can be the secret key, but I'll have a security requirement that, if I just use the hint as the secret key, then you can use the secret key to decrypt other ciphertexts as well. I haven't yet described the security property, and I'll do that, which will prevent that from happening.
So after you supply the hint, why can't we think of it as if that's directly to M, goes directly?
Yeah, because I'm requiring the hint to be much smaller than the message.
Ah, okay.
Good.
Yeah.
So great. So there are two
Good.
non-triviality requirements. One is the efficiency one, which Shafi asked, and the other is the security requirement, which Akshay asked. And I'm going to explain the security requirement on the next slide. Okay. So let me answer the security requirement. I think the questions are with respect to split FHE. So maybe this will answer. So the security requirement is as natural as you might expect. So given the hint, you should be able to decrypt the ciphertext, but you shouldn't be able to use it to decrypt other ciphertexts, right? So very roughly, what it says is, or if you have two messages M0, M1, and a circuit C, such that C of M0 is equal to C of M1, then so I generate the hint using either CM0 or CM1. You shouldn't be able to tell whether you're dealing with the ciphertext encrypting M0 or a ciphertext encrypting M1. So this should be in C0, H0, and C1, H1. So I'm also giving the ciphertext to the adversary. Sorry about that. So the adversary is given an encryption of M0 and a hint H0, or the adversary is given the ciphertext C1 or the hint H1, and it cannot tell which of the values it's given. Does it make sense? Okay, let me now see the question.
Does it imply circuit privacy as well? I mean,
no, because the circuit is the same in both cases.
Oh yeah, sure.
So let me see what the question is. So by heuristic, do you mean if you break split FHE, one does not necessarily, I need to expand this window. One does not necessarily break a construction on the left side? Yes, that's true. That's how I interpret it. Thanks. And the definition of split seems unrelated to eval, so it can be defined for any PK. Yes, that is also true. You can define it for any PK, and that's why we're going to define it also for linearly homomorphic encryption with split decryption. Okay. So is the definition of split FHE clear? It's a FHE scheme where I split the decryption process into two parts. That's the hint generation and the reconstruction. The hint generation generates a hint that allows you to decrypt the ciphertext, but the efficiency requirement is that the hint needs to be small, and the security requirement, very roughly, is you don't learn anything more than the ability to decrypt that cipher.
So the hints may be the same even.
Well,
they won't be the same, but
they won't be the same.
Is there a reason why they couldn't be the same?
I guess because well, you could have encryption schemes where where it might end up happening. But if you think about a natural encryption scheme, encryptions of M0 and M1 would have sort of live in distinct spaces. So if I compute this,
but the hint is only for decrypting the result of the circuit.
Yes. So it is possible that they might end up to be the same space, but it seems somewhat
unlikely. Okay.
Unlikely. Yeah.
Mm-hmm.
Regarding Hotek's question, that you can define the split property even without fully homomorphic encryption, but it looks like the security property for split FHE sort of inherently requires some kind of homomorphism. Do I read that right?
So the way I defined it, yes, but you could define it alternatively without, if you didn't have homomorphism, you could define it as saying, look, if I give you the hint with respect to a particular ciphertext, you shouldn't be able to learn anything else about other independently generated ciphertexts. In the case of FHE, because we're giving a hint about one ciphertext and where there are other ciphertexts where there's a computation, so maybe the property has to involve. Yes. Did I answer your question, Chris?
Yeah, I don't I don't know if I understand. Let's say the scheme doesn't support any homomorphism at all. So
then I
guess
would
the
have to
only
define it
circuits.
differently.
Okay. Okay. So
Yeah,
if the
but I
circuit
could
C
define
is the
the
only
split
circuit
property.
C
Yeah.
supported with the identity.
Yes.
Okay.
Yeah. Okay. So let me. So I can also define a stronger version of split FHE, which is something we will need for obfuscation, where instead of just giving one hint, where security holds, even if I give you a larger number of hints, many hints, starting with the same ciphertext. Okay. So very natural generalization. So this is something that we actually need, but for the rest of the talk, we'll sort of work with the weaker property and gloss over the reasons why we need the stronger property. Okay, so what we have defined so far is what split FHE is. Now let me tell you what the 3 ingredients that I'm using are. Okay, so the first ingredient I'm using is fully homomorphic encryption with linear decryption. This is something that we all know is just basically an FHE scheme with nearly linear decryption, wherein we say that the decryption algorithm is given a ciphertext is linear in the secret key. So in particular, I can take the ciphertext in its natural form or re-expressed such that the inner product of the secret key, again expressed in some suitable form with the ciphertext, yields the message with some small error e. Okay, so where the message is encoded with some kind of an error correcting code. For typical fully homomorphic encryption schemes, it could just be encoding it in, for example, the higher order bits of the output space, and this is what you get. So this is basically this linear or nearly linear decryption property holds virtually for all known FHE schemes. So we can take any of those schemes and plug it into our current construction, and we'll get a candidate for obfuscation. Okay? So this is the first thing. Are there any questions? I see there are some questions. Yeah, okay. I think that was just answering some questions. Okay. Get back to the slides.
So Sanjam, just to clarify the split decryption, this thing, you don't have any bounds on the circuit complexity of the decryption circuits in this thing. Just the size of the hint should be small.
Yeah, just the size of the hint should be small.
The stage 1 and stage 2 decryption algorithms,
no.
They need not be.
Yeah, they don't need. Okay, so I already defined the split property for FHE. I can similarly define the split property for a linearly homomorphic encryption scheme. And to give you just to give you an example of such a linearly homomorphic encryption scheme with split decryption, something that was already studied in the literature is the Damgard-Zurich encryption scheme. So a Damgard-Zurich encryption scheme consists of the public parameter n, which is the product of 2 large primes, or RSA modulus, a public key, which is n and zeta, a large constant, say greater than 1, and the encryption algorithm corresponds to encrypting a message m corresponds to taking a randomness r in zn and a message m in zn to the eta. So the message space is much larger than the randomness space that's used to generate the ciphertext, and the encryption is generated by computing this equation, which is r to the n to the zeta times 1 plus n to the m mod n zeta plus 1. Okay, so that's the encryption algorithm for Damgard-Zurich, and it's easy to observe that it has linearly homomorphic properties. So if you take 2 ciphertexts and you multiply them, you see that the randomnesses get multiplied and gathered together, and the second part of the ciphertext consists of 1 plus n to the power m, and this part also gets multiplied, and you get m1 plus m2 in the exponent. So you get an encryption of the sum of the messages under a new randomness. So it has the linear homomorphic property that's desired. But what's nice is that this encryption scheme also comes with split decryption. In particular, I can break the decryption algorithm into 2 parts. The first generates the hint. In particular, for any ciphertext, if I disclose the randomness r, then you can use that to learn what the message m is, because you can remove the r to the n to the zeta part and then recover the message m from whatever is left over. And so this is exactly what my hint is going to be. So given a ciphertext, I can compute c to the n to the minus theta. And if you do the computation, it corresponds just to r mod n. And once r mod n is provided, anybody can use it to decrypt a ciphertext without any knowledge of the secret key. And it should sort of roughly have the security property that was desired, because I'm effectively leaking the randomness that was used to generate one ciphertext. I'm not leaking anything about the secret key, so nothing should be leaked. Okay. With regard to the efficiency property, observe that the value rho comes from Zn, which is much smaller than the message space, which comes from Zn to the power zeta, where zeta is, if it's large enough, it's going to be much larger than Zn. So my message is going to be much larger than the randomness, and so I get both the desired security and efficiency property.
So that's why you don't use like Parier or something.
Yes.
I have a question for you. So is this why they introduced this system? Because of this?
Yes, because they didn't talk. I think they didn't care about the split decryption. What they cared about was the efficiency, that you get the homomorphic encryption with rate 1. In particular, the size of the ciphertext is roughly the same as the size of the message, and additionally, you can perform linear homomorphism on top of it.
Okay, thanks. When was this from? When is this from?
I don't remember the year. Maybe I don't know. Maybe someone in the before my time. So I don't remember the.
It was around 2004 or so.
Yeah.
So linear homomorphism was of value for some application. Okay.
Yeah. Also the efficiency, because you get shorter ciphertext. Okay. So
this Sanjam?
Yeah.
The security property for split. This is something you can actually prove. It's not a heuristic assumption about it.
Yeah.
Great. Thanks.
Okay. So now that we have linear homomorphic split decryption, we all know, and you can also get a construction from LWE if you wanted, but that's sort of a construction that we have in the paper. I wanted to give examples of these things which existed in the literature prior to our work. Okay, so then we also have cryptographic hash functions. We know how to construct hash functions. You can also use homomorphic encryption schemes to construct it. And as a heads up, we're going to model the hash function as a random oracle in our construction. Okay, so now that all the definitions in this picture are complete, let me give you the step from going from split, the step in going from split FHE to indistinguishability obfuscation. That's sort of the easy step, and then we'll see the heuristic step. And I'll just do it in one slide and give you the high level idea for it, and then you can look at the paper for details.
So Sanjam, just to make sure from this previous slide, so you're saying that all these three boxes you can get under LWE?
Yes.
Okay. So that part, there's nothing heuristic at this point.
Well, there is circular security that is heuristic. You're going to have to assume that FHE,
okay.
that part is heuristic.
And you do need the fully.
Yes, we're going to use circular security in even more involved way. So the heuristic also is going to push in its own forms of circular security, but we'll see that in a second. But so far, what I've said, the only heuristic part is fully homomorphic encryption. Yeah.
Okay.
Yeah. The step from going from split FHE to IO is actually fairly easy. I mean, there's some details I'm going to skip here since it's anyway provable. But just to give you an idea how it works, is that what I can do is I can use split FHE to compress a truth table for a function f. How could I do that? Well, I could give you so the compressed version of the truth table is going to consist of an encryption of the function description or the circuit description for f, and a hint h for decrypting the following ciphertext, which is written in red on the slide. It consists of encryption of pk of f1 all the way to f2 to the lambda, where lambda is the input length. Okay, so this is I give it as the hint for this, and observe that the hint is going to be much smaller than the ciphertext. And if the decryption of the circuit f is small, I'm essentially compressing the truth table of the function f into something much smaller. Okay? And given the hint, you can recover the entire truth table. Given the ciphertext encryption of F and the hint, you can first compute the entire encrypted truth table and then use the hint to decrypt it and recover the hint. And as shown by Lin et al., this is something that's enough to construct IO. Assume LWE and IO, and this primitive, what they call XIO in their paper, we can get indistinguishability obfuscation. An alternative way would be to use functional encryption from GKPVZ, and one could get IO that way as well. And that would give you a construction of FE schemes, and from there you could then instantiate. You could go further by Bitansky, Vaikunthathan, or Ananthan Jain and get obfuscation. I see some questions. So in the constructions, it is totally independent of the message size. Does it? I think it just needs to be smaller, but I'll have to double check. But in the construction, it is just much smaller. I think it's just much smaller. Okay, so let me move on to the more interesting part, which is how do we
Sanjam,
use...
sorry,
Yes.
I have a question. So you said that this isn't quite formal. There's something missing. Like this looks pretty convincing to me on this slide.
Yeah,
Can you say a little about what's being sought?
Good. So in the construction, you need to this thing needs to be repeated many times, and you have to amortize the size of the public key in a split FHE could be large, so you have to amortize that cost as well. So you need that stronger security that I mentioned for split FHE before. But I'm not going. Does that make some? I hope that makes some sense. I don't want to go too much into it, but it's a sense. This makes sense. It's just that the public key could be large, and to accommodate for the fact you have to do a little more. And that's why you need the stronger security for a split FHE that I mentioned before.
Got it. Thanks.
Okay.
I'm still a bit confused. The hints sort of depend on the ciphertext. How do you recompute the ciphertext? Don't you need the randomness for the original ciphertext or some weird thing like that?
No. So given a ciphertext, this is if it's a this is an FHE scheme. So given an encryption of F, you can compute whatever you want.
I see.
So you run the evaluation algorithm. So I start with a small ciphertext. You run an eval and produce this gigantic ciphertext.
I see.
That's something everybody can do.
Right.
And now I give the hint for this gigantic ciphertext. But since the hint is small, you can now compute the gigantic ciphertext yourself and decrypt it using this small hint that I gave.
I see. Thanks. Yeah.
Okay. Great. Thanks for the question. Yes.
The other question is,
yes.
Why does it? So why do you need to go through the intermediate step of the non-trivial I/O instead of doing I/O directly?
Well, I mean, I don't fully understand the question, but
So I have a proposal. So from my understanding, the current obfuscation scheme is the encryption of the function and the hint.
yes.
So why don't I just encrypt the function which take a normal input size and
Oh, good, fantastic. So I think to generate the hint, I have to first generate the entire encryption.
entire encryption meaning that F1 to F2 to the lambda?
Yes. So now then generating the obfuscation would be extremely expensive. It would take a long time, and also it'll take a long time to compute the output. It wouldn't be polynomial anymore.
So just another question. So would it give at least a candidate if you can do the obfuscation? For example, the obfuscation time take exponential time, but the final output is polynomial.
Yes, you could. Probably will work. Yes.
So the size is not the problem.
The size is not the problem. It's just the computation. Computation time. Yes.
Okay. Thank you.
Good. Great question. So now we have seen all the well understood and the provable parts. Let me get to the heuristic, which is sort of the interesting part here. Okay, so the first attempt is going to be as follows. So what I'm going to do is I'm going to publish these public parameters that are going to consist of the public key of an FHE scheme, the public key of the linearly homomorphic scheme, and I'm going to give an encryption of the secret key of an FHE scheme under the linearly homomorphic encryption scheme. Okay, so these are the three parameters that I publish, and yeah. So now let's say that I'm trying to construct a split FHE. Let's say I have an encryption of a large or a long length message M. Under the FHE scheme, I would like to give a hint enabling the decryption. So here's a quick idea. I have two encryption schemes which have sort of varying properties. One is a fully homomorphic, and the other is a linear homomorphic with split decryption. What if I put them two together? Can I immediately get sort of a split FHE scheme? Well, to some extent, yes, right? So I can immediately take a ciphertext under the FHE scheme, do a key switch, get an encryption of the message under the linearly homomorphic encryption scheme. And then once I have the ciphertext under the linearly homomorphic encryption scheme, I could give a hint just for the linearly homomorphic encryption scheme that would allow you to decode error correcting encoding of the message M plus the error. Once you recover that, you can recover the message from that. Okay, so let me repeat, and if there are questions, I can answer. So what I'm doing is I have two encryption schemes. One is fully homomorphic, the other is linearly homomorphic, but additionally comes with split decryption. So I'm going to put the two together to get a fully homomorphic encryption with split FHE. And how I'm going to do that is that anytime I need to give a hint, I will first do a key switch to the linearly homomorphic encryption scheme and give a hint for the linearly homomorphic encryption scheme because it was already had the split property, right? And I can do this key switch from the fully homomorphic to the linearly homomorphic encryption scheme because the decryption algorithm of the fully homomorphic encryption scheme is linear. Okay? So that's the, is that clear? Questions on this?
So does LHE.encryption have PK of LHE or not FHE?
Yes, sorry, this is a typo. This should be PK of LHE. Okay, any more questions? So let me see. I think there were some questions in the chat window.
They got clarified.
Okay, fantastic. Okay, so you might ask, well, is it already enough? Well, the problem is that if I give this hint, this hint allows anybody to learn ECC of M plus E, from which effectively leaks some information about E and potentially also about the secret key of the FHE scheme, right? So in particular, if I give multiple hints, it gives you a bunch of linear equations in the secret key of the FHE scheme, and you could solve those linear equations to get the SKFHE out. So this is, while it does get the efficiency property that's desired, it doesn't get the desired security property. In particular, if I give multiple hints, I can leak the secret key of the FHE scheme. Well, how could I fix it? This is an idea that's used, at several places in sort of trying to hide the error for FHE schemes. And the idea is to sort of use some kind of a noise smudging. So what if I had access to an oracle and looking ahead, this is where random oracle is going to come into play, that gave me an encryption of something small under the linearly homomorphic encryption scheme, which is small but much larger than the error that ends up in the size of the error E. Then I could have just added these two ciphertexts and given a hint for these two, the sum of these two ciphertexts rather than just the original ciphertext. Does it make sense? If I had access to some way of sampling these small, these linearly homomorphic encryption ciphertexts of small random values, then I would be good to go. And I couldn't do this via a random oracle. I could plug in where the random oracle would be queried on the ciphertext for which I'm trying to give the hint, and then I get this ciphertext, and I could do this noise smudging and give the hint, and that would be all. Using it, you could still recover the message M, because E plus S is not going to be as large, but it's going to prevent the attack that was highlighted on the previous slide, which is that you could learn the secret key given multiple hints. Okay? So this is a very natural idea. The problem is that we do not have this oracle. In particular, the linear homomorphic encryption scheme does not have, it's not possible to sample ciphertext which encrypt small random values. Okay, so that's a problem. So we do not have this oracle. As a side note, if we did have access to this this oracle, we can actually get a provably secure construction for split FHE in the random oracle model. And you can, an alternative way of thinking of the result at this point is, well, this can be thought of as a completeness result. If you have a mechanism for sampling encryptions of short, small random values, then that's enough to realize obfuscation. But since we don't have it, we're going to sort of build a heuristic around it to make it happen. So how are we going to do it? So note that we do not have a mechanism to sample encryptions of small values, but the Damgard-Zurich scheme that I showed you does have the property that the ciphertexts are pseudo-random. So we could sample random ciphertext encrypting random values, not just small random values. So of course, if I plug in a small, instead of a small random value, just a large random value here, then I'm in trouble, because this is going to not just flood the error, but also the message. And therefore, the hint is going to be useless. So we want to somehow use this ciphertext that encrypts a large random value and convert it into something that's encrypts a small random value. Well, how could we do that? Well, we have FHE to our rescue. So what we're going to do is we're going to, in addition to the public parameters, so previously we had just encrypted the secret key of the FHE scheme under the linearly homomorphic encryption scheme. Now I'm also going to give an encryption of the secret key of the linearly homomorphic encryption scheme under the FHE scheme. Okay, so we know, so we're going to assume circular security between the FHE and the linearly homomorphic encryption scheme. So I'm going to give the secret key of the FHE scheme under the linear homomorphic encryption, the secret key of the linearly homomorphic under the FHE scheme. Okay, so this is where I'm adding this circularity. If I have additional access to this parameter and I have access to encryption of a large random value R under the linearly homomorphic encryption scheme, I can do a key switch and move it to an FHE scheme, right? So if I have, because I have an encryption of the secret key of the linearly homomorphic encryption scheme, I could decrypt the linearly homomorphic encryption ciphertext under the FHE. Now that I have encryption of R under the FHE, I could remove the higher order bits. Because it's an FHE, I could compute arbitrary circuits and also remove the higher order bits, and I get the lower order bits of R in the FHE. Now that I have the lower order bits, I can decrypt, do the key switch back to the linearly homomorphic encryption scheme, and I get an encryption of the lower order bits plus some noise, which results from the decryption process. Is this making sense? So what I've achieved is I had an encryption of something random under the linearly homomorphic encryption scheme. And what I've ended up with is an encryption of the lower order bits of the random value plus some noise under the linearly homomorphic encryption scheme. And how I've done it is by, I couldn't compute arbitrary circuits on R. So I first moved it to FHE, did the arbitrary computation, and brought it back to linearly homomorphic. Is this making sense?
Wouldn't you get an error corrected version of R LSBs plus noise?
Yeah, so I'm thinking of it being encoded in the higher order bits plus noise. It only affects the lower order bits.
Also,
so the higher order bits are already zero there.
Also, why couldn't you just start with the randomness being in under the FHE hood? Why did you?
Because the ciphertexts that there are not efficiently sampleable. I can only sample the ciphertext corresponding to the linearly homomorphic encryption as the out. So, you know, for the random oracle, if I feed something, it gives me a random string. The random string has to be from the range of the ciphertext space, right?
Okay.
For the linearly homomorphic encryption scheme, that property is satisfied, not for the FHE scheme.
So what's the hint here? Is this RLSB?
No, so this is the encrypted value. Now, once I get the ciphertext, I've essentially gotten encryption of something small.
Yeah.
So now what I'm going to do is I'm going to use this small and add it to the ECC M plus E and give the hint for that ciphertext. Does it make sense?
Okay, so the hint is for the ciphertext, which is the error correction of M plus error plus these RLSBs. Yeah.
Exactly. Yeah.
Mm-hmm.
So now, given this hint, you could recover the higher order bits of the message M, and we're hoping here, and this is the heuristic part, that you know, because we did this sort of mumbo jumbo on R, and it's highly nonlinear, we don't know what's happening, and this is sort of something inspired by the bootstrapping in FHE, right? So there, when you do bootstrapping, we don't know what's happening. It's highly nonlinear. That this RLSB, the error in RLSB is unrelated to the secret key and are in enough of a way that it hides E and the secret key. So just given the hint, you can't recover the secret key. Okay. So that's sort of the heuristic part in the construction. And once you have this, this is sort of the entire construction. And this is the split FHE scheme. We don't know attacks against it, and sort of the intuition for that arises from the fact that this computation is highly nonlinear because there's a you know, FHE bootstrappings that are happening along the way, and so on. And then you know, the further you can make this even more nonlinear by introducing more FHE bootstrapping, and this is shown to be in other contexts useful, for example, to achieve circuit privacy. We don't have a proof for this, but that's the heuristic here.
Sanjam, just to clarify, so this heuristic part, you could actually, it would be provably secure in the random oracle model under the circularity assumption, or you need more, you need something else?
No. So if I had an oracle, you know, the random oracle gave encryptions of something small, that would be provably secure in the random oracle model. But the oracle only gives encryptions of something random. So to bring it to something small, I do it this, you know, I first convert it to FHE and then bring it back to LHE.
Right.
That part is, you know, heuristic. That's essentially the heuristic part, right? That this RLSB, you know, it's not RLSB. It's RLSB some noise. We're relying on the fact that the noise in itself does not, you know, cancel some of the lower order bits of RLSB. Does it make sense?
Yes.
So that's sort of the heuristic that, you know, when I do this, there's going to be noise there. That noise shouldn't somehow be weirdly correlated with RLSB itself to be such that when I give a hint, the thing leaks relationships of the secret key.
So the point is that RLSB is big enough that it really hides E. It smudges out like it hides, but there's some additional noise in the RLSB that's pretty large, and that's
which is pretty large, and we don't know what that is, and it's clearly non-linear. It's not linear. We can further make, you know, weaken the relationship by doing additional bootstrappings along the way and so on. But that, you know, that we don't know if it would help or not help. And that's sort of the heuristic part in the construction. Okay, so that's you know, that's basically the construction. Once you assume this is split FHE, then the obfuscation construction you get is provably secure. And in sort of the heuristic part lies in taking a ciphertext that encrypts something large to converting something to something that's small. It's either some questions.
There's just some discussion happening.
Yeah, so sorry if I missed, where do you use the random oracle? So the random oracle is used to sample this encryption of a large random, you know, the ciphertext star. So, you know, if you want to give a hint for encryption for this value, you feed it to the random oracle, and out comes this random ciphertext, which you do this heuristic step, add it to the key switch to value and give the hint for that. So there will be a different you know, randomization factor for each ciphertext for which the hint is being provided. Okay, so this completes the, if there are any questions, let me see. Oh, there are more in the chat. Yeah, so the random oracle is used because these ciphertexts are going to be much larger. So you feed the random oracle a small string, and then it spits out potentially a much larger ciphertext out. Okay, so to summarize, prior constructions on obfuscation relied on new assumptions, and while the assumptions were new, the constructions were provably secure. So you started with a new assumption, gave a provably secure construction based on that. In contrast, what we're doing here is we're starting with standard crypto primitives that were started in the past. We knew constructions for these in the literature. However, we combine them in a heuristic way to get a construction that we conjecture is secure. So it's the construction which is heuristic. I think that these are of very different flavor. While the construction in the first side need more cryptanalysis, it's sort of in the kind of attacks we expect to have could completely devastate the scheme. In contrast, I think that the new candidate we have, it doesn't necessarily just present one candidate. It's sort of a family of candidates, and if the scheme ends up being broken, it would be weird to see a correlation between FHE schemes and things based on DCR. So sort of these are very different assumptions, and if it's a heuristic that combines the two. And for the scheme to be broken, it would have to use some properties that sort of use them both in a natural way. And then also, if the scheme ends up being broken, perhaps it will give us insights into the security of FHE schemes itself, which also rely on the circular security heuristic. So this is something that needs further investigation and needs a lot of work. So to summarize, prior works used new ingredients to realize obfuscation. In this work, we use known ingredients, but we have a new recipe for realizing obfuscation. So that's all I wanted to say. So this and this comes with inherent simplicity for the scheme. See, also, finally, I would like to remark that while I presented just the IO scheme, the idea is where we can replace the random oracle with additional communication. It's possible to get other applications without any heuristic. So it helps improve the some of the applications where we can get new results without any heuristics. So the techniques are useful besides the context of IO as well. So that's all I wanted to say. Let me see, there are some questions. Oh, I see. I think Nico answered. Thanks.
So,
Nico. Yeah.
First of all, people can unmute and just
yes.
thanks Sanjam for the wonderful talk.
Great.
And yeah, I think at this point, people can just feel free to unmute themselves and ask questions.
I have a question about I think there's one version which is described using the random oracle. So what's the input of the random oracle?
So the ciphertext for which you're trying to give the hint.
The ciphertext you are trying to give the hint is the input of the random oracle. Okay. Are there any variants? Like, is that the only option that you take the ciphertext?
Well, you could give it the linearly homomorphic encryption, the value after the key switch to the random oracle as well.
Could you say that again? Like, what's the other?
If I'm trying to, if on the slide that you see on the screen, if I'm trying to give the hint for the ciphertext that encrypts the message M, then I want a fresh, randomizing term for this ciphertext. I could give the random oracle this ciphertext and get a hint, or I could do the key switching and then give the hint, right? I could in fact use any intermediate step of the computation as input to the random oracle. I mean, I'm just using the starting point.
Gotcha, thanks.
One sort of like a side question thing.
Yeah.
So So, okay, this is one mechanism of sort of trying to smudge the noise in a sense.
Yes.
Is it possible, again, this will be heuristic, but these low complexity PRGs, these have the assumptions like noise smudging generators or all these pseudo projects generators or something.
Yeah.
So, okay, let's assume that that is secure. That assumption holds. Can you use that assumption to just add the smudging noise in the linearly homomorphic encryption ciphertext and not doing this business of doing the random oracle adding and just smudging it in a different way? Basically, give out the seed of the pseudo-random generator as part of the ciphertext, and then also evaluate that homomorphically, and then that will automatically smudge it out.
No, I think so. So I think there are sort of two questions, right? So one is, can we replace this heuristic with the assumptions that are used in that context, and perhaps maybe we'll get a simple construction or something like that. You know, that's totally plausible. I don't know how to do that. And maybe the second question you're asking is, if I just use, you know, because we have full FHE at our disposal, we don't have to use these low depth PRGs. I could just give an encryption of a PRG seed and use that and expand it and use that to decrypt. The problem is that if I do that, then, you know, ultimately it's just going to be these linear functions. And I would be worried about things canceling. You know, if it just ends up being linear equation in the secret key, that would be problematic. Right? So you want these fresh ciphertexts that are sampled to be non-linear in the
oh, I see. Maybe the issue is that the noise that you leak in that case, that will leak the original seed itself.
Yes, precisely.
Okay. Yeah, okay. So,
but at the same time, one thing to note here is that you know, the PR. So there's one big distinction between previous IO approaches and this approach, is that in you know, prior works, you had an obfuscation that the noise that was being added, and this is true also about the mmap things, is when you spit out something, there was a noise there, and you know, you could try to solve linear equations and learn something. But in this case, what's happening is, you know, we're computing, everything can be computed inside the belly of the beast, right? Because you have full FHE, and so you can sort of compute fresh values there and try to, so you don't have to work with sort of these low depth PRGs and so on.
And also, one other question. So the heuristic that you mentioned, I was just asking. Yeah, I was just asking the.
Yeah. Okay.
I was just asking that. So you mentioned about this heuristic of using the random oracle to sample ciphertext obliviously, which such that they have small messages.
Yeah.
Possibly you can just also use IO just to instantiate that. I mean.
Yeah. So basically,
it won't give you any.
But of course, if you have that, then would be good. And what we're presenting is sort of like this heuristic way of sampling ciphertext with small, where the encrypted message is small. And if you could do it, that gives you IO. And that's basically the heuristic part, because, you know, if you instantiate that itself as oracle, then you can get a provably secure solution.
I was just wondering that the random oracle and the function that's computing this ciphertext, that can itself be imagined like a obfuscated program, but maybe for a very small class of functions.
Oh yeah, definitely.
So,
and then
so I was thinking that maybe
yeah. You can, so that's sort of, you can think of it as a completeness thing, that if you have obfuscation for this thing, then you can obfuscate all circuits based on that.
But that class doesn't seem like a class of evasive functions, right? That does seem like you're computing.
Yeah, it's not evasive function, but it is sort of simpler in some other sense.
So, yeah, okay.
A question about a possible attack avenue. Maybe you can tell me this doesn't make sense. So you have the fully homomorphic encryption of the LHE secret key, right?
Yeah.
And then you're doing like kind of a bootstrapping on this secret key, and then that's going to have some noise in it, and the noise, you know, evolves in some way. And then at the end, the hint essentially reveals this kind of evolved noise or something very close to it, right?
Yes.
So if you, and I suppose this will be done many times or something like that. So if you can somehow reconstruct the original noise or learn something about the original noise in the encryption of the LHG secret key, then maybe you can recover the LHG secret key or something. That's a route you could try. And do we have,
definitely. Yeah, that's a route that seems to be, if you could, sounds.
There's some high, there's some high depth. There's some high depth function being applied to the noise in the original FHE. Okay. Yep.
And you can make it even, higher depth, right? By maybe applying bootstrapping after every step. Right. And that makes it look like, well, it seems hard, but I don't have a good justification. Yeah.
Okay. Thanks.
Great.
So why do we need to start with a fully homomorphic encryption instead of just leveled at the first place?
Let's see. Well, I mean, ultimately we will get a FHE because I'm giving the secret key of one under the other and the other, and so, right? So I'm giving the secret key of the FHE under the LHE. So if that's the case, then I can use these two to get a secret key of the FHE under the FHE. So, but if your question is why can we get rid of the FHE I guess I already would know the depth of the circuit, so I could set the parameters such that I could start with, but ultimately you would get FHE because you're giving an encryption of the FHE under the LHE.
So, if people have any more questions, now is the time.
Sanjam, you mentioned you could use LW-based LHE. Would you also get the dense ciphertext property like this? Would you be able to use it for the whole thing, or?
So that would be needed for the construction.
Okay.
So you said that this DG construction that is already has the property of it's linearly homomorphic. I mean, is it even good enough to think about homomorphic encryption, which has the split property, but maybe for slightly more expressive functions that you can evaluate, and maybe that way. Right now you require that the homomorphic encryption scheme that has split decryption is only linearly homomorphic. But that puts other constraints on the remaining components of the entire construction. So maybe if you can say, okay, split decryption, and homomorphic encryption system, which is slightly, which can maybe evaluate like linear additions plus maybe one multiplication. But then you put less constraints on the other parts of the entire this mixing schema. Is that?
So the two assumptions which we know how to do these things are LWE and DCR, and there we both get this additional property. So it's unclear.
Okay. So I guess if there are no other questions, let's just thank Sanjam for the wonderful talk, and people can unmute themselves, but not right now. And thanks everybody for joining in today. And next week we'll just have our last talk of the Lattice seminar series, and I'll see you all then. Thank you for coming today. I'll stop the recording. Sorry.